If I were to ask you where the southernmost point of the world is, you would rightly say the South Pole, because this place is located at 90 degrees south latitude. So can a person at the South Pole go any further south? No, that's not possible, because the direction of south ends right here. In other words, it loses its meaning. So can't we say something similar for the beginning of the universe? To do that, we need to rewind the film a little, or actually quite a lot. 13.8 billion years ago. In other words, let's go to the very beginning of the story. After all, every great story has a beginning. But when we get to that first moment, something interesting happens. The film breaks and the screen goes dark. None of the equations work. Even the laws of physics are rendered helpless. So could this point be a boundary? If that's the case, was there nothing before it? Was the universe born from this nothingness? For thousands of years, from scientists to philosophers, from poets to dervishes, the same question has always been asked. In fact, even in the minds of ordinary people like you and me, that question is always there. What was there before the beginning? This question also puzzled one of the world's brightest minds, Stephen Hawking. To reach the answer, he used the most powerful tools available. In his toolbox, he had the general theory of relativity developed by another of the world's brightest minds, Albert Einstein, mathematical equations, and classical cosmology based on observation. However, using all of these to rewind the universe, he hit a wall called a singularity. It's a wall that we just can't seem to get past. Because here, neither mathematics nor the laws of physics apply. So who paved the way to this wall? Ironically, it was the person who never wanted to go down that path, Albert Einstein. He didn't like this idea at all, because the universe he imagined was infinite and static. In other words, he believed in a universe without a beginning. But as we get closer to the Big Bang, space shrinks to an infinite degree. Time almost comes to a standstill. All the equations lose their meaning. Naturally, the tools Hawking used also become useless. Realizing he couldn't reach a conclusion this way, Hawking proposed a provocative idea in 1983. Perhaps the only initial condition is that there are no initial conditions. Perhaps the universe has no boundary. So, seeing that classical physics wasn't working, Hawking took another tool out of his toolbox: quantum mechanics. In other words, he tried to understand the universe through the laws of quantum mechanics. This is called quantum cosmology. To support this new idea, which he called the no boundary proposal, Hawking uses the map analogy I mentioned at the beginning of the video. Yes, I admit I copied from him. Asking what was before the Big Bang is as meaningless as asking what is south of the South Pole, says Hawking. In other words, at the moment of the Big Bang, time, just like the concept of direction, loses its meaning. In such a situation, it's not possible to talk about a before, because what we call before is also a situation related to time. So there's not even a concept of time to use as a reference here. Hawking eventually said maybe we should abandon this idea of a beginning that resembles an explosion, because there may not be a starting point like we imagine. Maybe time is behaving like another dimension of space. He called this time that behaves like space imaginary time. Thanks to this idea, that problematic starting point was removed from the equations and a smooth, closed surface took its place. So if we put time into a mathematical form, could we possibly eliminate that wall of singularity? If the universe really started this way, it must have left some patterns in today's universe after the Big Bang. For years, scientists have been searching for these traces in the cosmic microwave background radiation, but they still haven't been found. The world of physics has also produced other theories to overcome this problem of the beginning. One of them is string theory. According to this theory, there may be other dimensions of space that we cannot see. Let's imagine it like this. You can think of the three-dimensional universe we know as a giant sheet suspended within those different dimensions. In this model, our sheet universe is not alone. Just like other sheets hanging side by side on a clothesline, there could be other parallel sheet universes. According to string theory, the Big Bang was the result of a collision between two of these massive universes. So this theory eliminates the singularity and replaces it with a physical collision. But be careful, it doesn't solve the problem. It just replaces it with bigger questions. Where were those sheet universes in the first place? What put them on a collision course? Where did that higher dimension they float in come from itself? There are no answers to these questions. Another theory about the beginning of the universe is the cyclical universe model. In fact, one of the biggest proponents of this model is Nobel laureate physicist Roger Penrose. Followers of this channel have probably heard his name often in previous videos. Penrose says the beginning of the universe could be the end of another universe. According to him, our universe will expand for trillions, quadrillions of years. All the stars will burn out, all the black holes will evaporate, and all that will be left is a cold, empty, and incredibly sparse sea of photons. According to the theory, this universe, filled with light but containing no matter, begins to behave just like the universe at the moment of its beginning. So the universe doesn't actually disappear, it just changes its form. Like the phoenix in legends, it is reborn from its own ashes forever. So all these theories trying to understand the beginning of the universe, no matter which path they take, eventually hit a wall. Some accept the existence of that wall, while others ignore it and just try to change its shape. But the result is always the same. The beginning of the universe is a dark area for today's physics, and we don't know what's behind this wall. Hawking's universe with no beginning, string theory's colliding universes, Roger Penrose's cyclical universe model. These were brilliant ideas, let's admit it. But all these theories always avoided the fundamental question. Can a universe be born from zero, from absolute nothingness? What if there was really nothing before our universe was formed? What if we're talking about nothingness in the truest sense? No matter, no energy, no time, and no space. Can you imagine a place where there is nothing? This is where we reach the limits of the human mind. It's impossible to imagine such a thing, my friends, and that's where the real strangeness begins. That's why physicists have tried to solve this with another strangeness. In other words, they've used a law of physics that can explain not what exists, but what doesn't exist. In fact, this was a tool that Hawking also used when he proposed his no-boundary thesis, quantum physics. If you recall, Hawking tried to eliminate the beginning by using this tool. So what does quantum physics say about nothingness? There are two approaches to this subject. First, what we describe as nothingness may not be completely nothing, because according to one interpretation of quantum physics, even a vacuum is not actually completely empty. In the vacuum of space, there's constant movement on a scale so small we can't see it with the naked eye. These are called virtual particles, because they aren't like measurable matter. They're just instantaneous energy fluctuations at the quantum level. They appear for a tiny fraction of a second and then immediately disappear. Some physicists think that one of these fluctuations might have momentarily grown and started the entire universe. It sounds like a crazy idea, doesn't it? A flicker within nothingness could have started a whole universe. But is this really a beginning that comes from nothingness? If you pay attention, even in this scenario, there is a quantum vacuum. So there is something there. So could there be a beginning that comes not from something, but from nothing? In other words, could the universe have truly been born from absolute nothingness? One of the boldest answers to this question in modern cosmology was given by physicist Alexander Vilenkin. He said that the universe may have come into existence from nothingness through quantum tunneling. So in the beginning, there was no space, no time, and no matter. There was only a potential that allowed the universe to be born. That is the most fundamental probability laws of quantum mechanics. According to Vilenkin, this is the closest point to nothingness that we can physically imagine. But how can the universe exist from such nothingness? I don't know about you, but my mind just can't grasp it. When quantum particles go from one place to another, they don't just move like a point. They have a probability distribution. So particles can be in many places, not just one. Even if there's an impassable energy barrier in front of them, this probability cloud spreads to the other side of the barrier, and sometimes they really do appear there, as if they pass right through it. Let me give you a more concrete example. Let's say you have a ball in your hand, and in front of you there's a wall so high that the ball can't get over it. No matter how many times you throw the ball at the wall, according to the rules of classical physics, the probability of the ball passing to the other side of the wall is zero. But in the quantum world, there is a probability that the ball will suddenly appear behind the wall without ever touching it. So the probability is not zero. The ball can pass through the wall as if it's tunneling through it. So Vilenkin took this mind-boggling idea and applied it to the universe itself. He said that the wall we call impassable is actually the state of the universe's non-existence. In other words, what we call absolute nothingness. Behind the wall is the state of existence. In other words, our universe. Quantum mechanics may have allowed the universe to tunnel from nothingness into existence by passing through that wall of non-existence. He's talking about a moment of origin born from probability. In other words, the universe might not have come out of something. Perhaps it emerged from nothing, without needing any cause, simply as a probability. Just as we can't know when a radioactive atom will decay, we can't know why and when the universe tunneled, says Vilenkin. So he's talking about an ultimate quantum event that doesn't need any trigger. Okay, but from nothingness, meaning zero energy, how could an energy-filled universe emerge, containing billions of stars, trillions, or even quadrillions of galaxies? Isn't that against the conservation of energy, one of the most fundamental laws of physics? You know, energy couldn't be created from nothing. Some physicists have also answered this. They say that the total energy of the universe is exactly zero. Yes, zero. Imagine a completely flat, perfectly level terrain. Let this be our zero energy state. In other words, nothingness. Now imagine you take a shovel of dirt from this terrain and make a small hill right next to it. This hill, which is above the ground, is a positive thing, but at the same time you've created a hole where you took the dirt from. And that is a negative thing, which is below the ground. The volume of the hill and the volume of the hole are exactly equal to each other. In total, was there any change in the amount of dirt on the terrain? No, the total is still zero, just its shape changed. So, according to the zero energy universe hypothesis, all the matter and energy in the universe is like that hill made of dirt. In other words, they form the positive side of the equation. And gravity is the enormous hole opened in space-time for that matter to exist. So that forms the negative part of the equation. According to the theory, all the positive matter energy in the universe is exactly equal to all the negative energy created by gravity. Of course, this theory is a subject of heated debate among physicists. Many physicists say that this law cannot be applied to an entire expanding, dynamic universe. I don't know if you've noticed, these theories have a common obsession: time. All of them are forced to somehow demolish our understanding of time. So why is that? Why do the greatest minds in physics ignore one of our most basic intuitions, time, to understand the beginning of the universe? What we call the past consists of our memories and records. We know this. The future, on the other hand, stands before us merely as an expectation, a possibility. The only thing that truly exists is that brief moment of now that we are in. But what if the moment we call now doesn't actually move forward at all? Is time like a flowing river or a frozen lake? Well, the physicists who produced all these theories saw nothing about time when they looked at the first moments of the universe. The source of this is based on the most fundamental equation of quantum cosmology, the Wheeler-DeWitt equation, named after physicists John Wheeler and Bryce DeWitt. John Wheeler is a general relativity expert, and Bryce DeWitt is a quantum theorist. So one is a representative of classical physics, and the other of quantum physics. These two scientists thought of something like this. Could we possibly combine quantum mechanics with general relativity? In other words, can we use these two tools in the toolbox at the same time and explain the entire universe with a single equation? And they wrote that equation. But when they saw the result, they noticed something interesting. The concept of time was disappearing from the equation. It was as if time was behaving like something outside the universe. In physics, this is called the problem of time. That's why Hawking replaced time with an imaginary time. String theory bent timelines and moved them to extra dimensions. Penrose's cyclical universe conceived of time as a circle. Vilenkin's quantum tunneling, on the other hand, threw time out completely and suggested that the universe was born from nothingness. All these ideas were a search for a solution to the universe's problem of time. Now we come to the most fundamental and ruthless question. Can these theories be scientifically proven? Science has a golden rule that separates it from philosophy and belief: falsifiability. For a theory to be considered scientific, there must be a potential experiment or observation that could refute that theory. If we can't test an idea in any way, meaning there's no possibility of calling it wrong, then we can never know if it's right either. None of these theories are falsifiable with our current technology and understanding. Therefore, we have no chance of verifying them. We can't build a telescope that will observe a moment before the Big Bang. We can't design an experiment to see how the universe tunneled out of nothingness. At least for now. So if we can't really measure it, is this science or metaphysics? Such a question also comes to the forefront. Important theoretical physicists like Lee Smolin say that if our theories don't produce testable predictions, then what we're doing is no longer science, but a kind of mathematical philosophy. This is one of the biggest debates within modern physics itself. On one hand, there are brilliant theories thought to solve the secrets of the universe, and on the other, strong criticisms saying those theories deviate from the fundamental rules of science. Now, explaining it like this, you might feel pessimistic, but this isn't a dead end. I mean, physics didn't give up here, let's just say that. Besides, isn't that the most beautiful part of science? When scientists hit a wall, they don't just say the road is over and turn back. They look for different ways to overcome it. For example, they examine the cosmic microwave background radiation, the oldest light in the universe, like a detective. They're tracing different kinds of patterns that could support these theories. Also, they are searching for primordial gravitational waves left over from a moment even smaller than the first second of the universe. If these waves can be detected, perhaps we'll have a chance to understand which theory more accurately describes that first moment. Scientists aren't just looking at the sky to understand the beginning of the universe. Especially in the last few years, they have started to simulate the initial conditions of the universe in a lab setting using various tools, including quantum computers. For example, they're trying to mimic the process of tunneling from nothingness, which physicist Vilenkin mentioned, with supercooled atoms in the lab. These baby universe simulations are opening a brand new window for us to observe how those theories behave mathematically. In fact, just as I was preparing this video, some very fresh news came from the world of science. In an experiment at the University of Maryland, physicists managed to observe in a lab, for the first time in history, how the concept of imaginary time works mathematically. Of course, this is not exactly the same as the idea Hawking proposed for the beginning of the universe, but this experiment shows that the strange mathematical language he used is not just a fantasy. Meaning, at the core of nature, this could have a physical equivalent. Perhaps developments like this will one day open new doors for us to test other mysteries. So, what does all this searching, all these theories tell us at the end of the day? Maybe we'll never know who is right, or the answer to that question we've been asking for centuries. But I think there's something much more important than that, the question itself. Because the answers are always changing. Newton's universe was replaced by Einstein's universe. Einstein's was questioned by the quantum universes of Hawking and Vilenkin. Everything we accept as true today can evolve into something completely different with a single observation, a single equation. But at the center of all this change, the same question keeps coming up. Don't just dismiss it as a question. Thanks to that curiosity, we built telescopes, invented mathematics, and even discovered quantum mechanics. That was the power that took us far enough to imagine nothingness. Maybe the answer is hidden somewhere beyond the stars. We don't know. But the question is right here, right now, inside our minds. And maybe the answer we've been looking for all these years is the question itself.